So let me just recap this stuff really quickly here. So we have our complex power S is equal to the product of our RMS phasor voltage V times our complex conjugate of our RMS phasor current I. This is equal to Vm Im cosine theta V minus theta I plus J Vm Im, sine theta V minus theta I, or V effective, those shouldn't be M's, those should be effectives. I effective with an angle of theta V minus theta I. Let me add that extra info. So this is average power measured in watts. Reactive power measured in VARs. Apparent power measured in volt amperes. And our power factor angle. So this seems like an overwhelming amount of information. And I'm not saying that it isn't a lot of information, but for the most part, this is actually all stuff that your calculator can handle for you, right? So I would argue that you never actually need to memorize any of the equations that I've given here other than this guy. Because if you set your calculator in rectangular, or to give you the answer in rectangular form, it's giving you average power and reactive power. If you set your calculator to give you the answer in polar form, it's directly giving you apparent power and power factor angle. So all of those equations are nice and good, but if you know how to use your calculator and you can remember what the constituent parts of complex power are, they are entirely unnecessary. I am a person who's been doing this for 7 years academically and 3 or 4 years on top of that professionally, doing all of my work designing battery energy storage systems and all of that kind of good stuff. And whenever I'm doing any sort of complex power calculation, I literally always just use that one equation and then just take the part that I need. Okay. So one handy way that we can use to help us remember how all of these things are related is what's called the power triangle. So the power triangle is simply a graphical representation of these relationships. So if we put on our vertical axis, so this is for imaginary numbers, and on our horizontal axis, this is for real numbers. If we have any generic complex power S, then the projection onto the real axis is our average power. The projection onto the imaginary axis is our reactive power. The length of this complex power vector is our apparent power, and the angle formed between the horizontal axis and our complex power vector is our power factor angle, right? So we just have a very simple right triangle here that tells us S is equal to P plus JQ in rectangular form, or magnitude of S, angle theta S in polar form. Let's see, what do I want to do now? So let's talk about power factor. Okay. So power factor is a measure of the electrical efficiency. I'm going to put efficiency in quotes here. Of a system. And the reason why I'm putting efficiency in quotes is this isn't really a power out over power in type of efficiency like we are traditionally used to. So that's why I put quotes around it, okay? So our power factor is defined mathematically as the ratio of average power to apparent power. You gotta be kidding me. Okay, so average power to apparent power. So it effectively tells us what portion of our complex power is actually usable. If we look at our relationships up here for average power, we have V effective, I effective, cosine theta V minus theta I. Our apparent power relationship is just V effective over I effective. So if we divide P by the magnitude of S, all we're left with is the cosine of our power factor angle. Okay. So these are our mathematical relationships. We are going to use them extensively. So now let me tell you a bit about why power factor is so important. And for any of you guys that go work in an industrial setting, particularly with electrical engineers, this is a word that's going to come up a whole heck of a lot related to the site, related to any rotating electrical machinery, all of that kind of good stuff. Okay. So average power is what we as consumers pay for, right? So if we look at our electricity bill, or we look at our parents' electricity bill or whoever's, what we're paying for is effectively the average power multiplied by the total amount of time in the month, which gives us our energy consumed, okay? Apparent power is the power that the electric utility pays to produce. And so by that, I mean, like, they have to buy coal or natural gas or things like that. They have to pay for the infrastructure in as much as maintaining the transmission lines and all of that kind of good stuff. So they produce some amount of power, right? Which we're going to call our apparent power. We pay for the power that we consume or convert into heat. And then there's that leftover reactive power that's just getting sent back and forth between the source and the load, right? So even though they had to pay to generate that, because we don't pay to consume it, because it always gets sent right back to them, that is a loss to the electric utility, okay, from a monetary standpoint. So electric utilities would prefer that the power factor is something that is very close to 1, meaning that they're not generating a lot more electricity than is actually needed at any given time, okay? So if your power factor is particularly low, and the threshold, it depends on the electric utility, but it's usually somewhere between 95% and 97.5%, or 0.95 to 0.975. So anything lower than that, the electric utility says, I'm going to fine you, okay? Because you're wasting our money and you're wasting our resources effectively. There are ways around that fine, which are called power factor correction. We're going to talk about that quite a bit. Like, that's all we're going to talk about on Wednesday, actually, is power factor correction. But I just want us to get a better understanding of what exactly power factor is today, so that when we deal with power factor correction, it kind of makes sense. So since this is based on a cosine function, we have a maximum value of 1. a minimum value of -1, and then, you know, all of that kind of good stuff. Okay, so let's talk about a few things. So let's put things in terms of theta s. So let's start with for theta s is equal to 0 degrees. Okay. So what would our power factor be? 1. And this is what we will typically call a unity power factor. Okay. So what kind of load would result in a power factor of 1? So what kind of load would mean that theta s has to be 0 degrees? So
It's all real.
exactly right. So what would that be, Ashton? Not DC. No, the average power would be the same thing as the no reactive power. So what kind of elements do that? Resistor, exactly right. So this means that we have a purely resistive load. So R is greater than 0, and our reactance is exactly equal to 0. Okay. Now let's talk about when 0 degrees is less than theta s is less than 90 degrees. Okay. So in this case, our power factor will be somewhere between. So let me write it like this. 1 will be greater than our power factor, will be greater than 0. Okay. When theta s is a positive quantity, then we are going to have what's called a lagging power factor. And it is because our current is lagging our voltage in a system. So this means that we have an inductive load where R is greater than 0 and our reactance is also greater than 0. When theta s is exactly equal to 90 degrees, what's our power factor? What's cosine of 90? 0. Yep. So our power factor is exactly equal to 0, meaning we're operating at effectively no efficiency whatsoever, or all of our load is reactive. Okay. So for theta s is equal to 90 degrees, that means that we're dealing with a purely inductive load where our resistance is 0 and our reactance is positive. And we can go effectively in the opposite direction as well. So if 0 degrees is greater than theta s is greater than negative 90 degrees, this is where we have a power factor. So it's still going to be 1 is less than, or excuse me, greater than our power factor is greater than 0. But in this case, we're operating at a leading power factor because our power factor angle theta s is a negative quantity, meaning that our current is leading our voltage. So this is what happens for capacitive loads. So R is greater than 0 and X is less than 0. And then lastly, we have theta s is equal to negative 90 degrees, giving us a power factor exactly equal to 0. And this happens when we have a purely capacitive load. Where R is equal to 0 and our reactance is negative. So realistically, we might have angles between positive 90 and negative 90, right? So like right now, let me draw a quick graph here to try to better explain what I'm talking about. All of our theta s's are falling in these two quadrants, okay? It is absolutely possible for theta s to be in quadrant 2 or quadrant 3, but that would mean that we have negative resistance because that's the only way that that will ever happen. So for the intents and purposes of this class, we're only ever going to be dealing with things that lie in quadrant 1 and 4, like I've defined here. Negative resistance is definitely a possibility. As a fact, actually, these might be LED lights up in here, but our fluorescent ballasts that we use to power fluorescent lights, they actually operate like they have a negative resistance. Literally, all that means is that as you increase the voltage, the current is flowing in the opposite direction you would expect. That's all negative resistance means. But anyway, so we're gonna limit our cases to plus or minus 90 degrees as our maximum value instead of plus or minus 180 because we are not going to bother with the negative resistance cases in this class. Okay, so our power factor tells us a lot of different things, or our power factor angle tells us a lot of different things, right? We can tell just by looking at what the angle is or what the value of the power factor is, what type of load we have, whether it's purely resistive, purely inductive, purely capacitive, inductive, capacitive, all of that kind of stuff. So just to recap here, I want to make this super duper clear. Whenever our power factor is between 0 and 90 degrees, or excuse me, whenever our power factor angle is between 0 and 90 degrees, we are operating at a lagging power factor. Whenever our power factor angle is between 0 and negative 90, we are operating at a leading power factor. When our angle is 0 or plus or minus 90, we are not leading or lagging because we are either fully, we're operating at 100% efficiency or 0% efficiency from a power factor perspective. So there is no leading or lagging, okay? We need to be pushed beyond that unity case in order for us to hit leading or lagging. Any questions about power factor before I move on to something else? Yes, sir. Reactance. So that is the imaginary part of impedance, right? So we know, let me just put it up here in green. So impedance Z, expressed as a rectangular form complex number, has some resistance and some reactance. Whenever X is positive, we're dealing with inductance, and whenever X is negative, we're dealing with capacitance. Okay, so I guess the last thing that I want to talk to you all about for today is alternative relationships for complex power. So we know that S is equal to the RMS phasor voltage V multiplied by the RMS phasor current I conjugate. Okay. Now, this is going to be technically a new relationship. It's literally just Ohm's law. I will happily derive it if you need me to. But I'm going to say that our RMS phasor voltage V is going to be the same thing as our RMS phasor current I times our impedance Z. Now, we formally derive this for regular phasors, and so it shouldn't be any huge leap of the imagination to say that the exact same relationship should hold true for RMS phasors, because we're effectively just multiplying both sides of our phasor Ohm's law relationship by a factor of 1 over the square root of 2. And since both sides are multiplied by the same thing, we get this to come out of it, okay? So I can take these two relationships and smash them together, and that would allow me to calculate the complex power absorbed by a particular element or network, only knowing the voltage or only knowing the current. So instead of knowing both pieces of information, I can get away with only knowing one of them. So this is another one of those handy shortcuts that I'm trying to show to you guys, okay? So let's start with this guy here, right? So let's put everything in terms of voltage first, okay? So the voltage RMS phasor is going to get left alone. And now what we're going to do is we're going to reorganize our Ohm's law relationship to solve for I. So I think that I should be V over Z. And I'm going to conjugate this thing, okay? So when I perform the complex conjugate operation on a fraction or on a ratio, it's the same thing as if I had conjugated the numerator and conjugated the denominator. So that's going to look like V conjugate times V over Z conjugate. Well, what is V conjugate times V? The magnitude of it squared. Ashton, I want to thank you. You're literally, I've taught this class 22 times or something ridiculous like that, and you're the first person that remembered that damn identity other than me. So great job. So that is literally just the magnitude of our RMS phasor voltage squared divided by the conjugate of the impedance. So we don't even need to know the phase angle of the voltage. We just need to know its magnitude and the impedance itself, and that's good enough to calculate complex power. So less information required than you would expect. We can do something very similar for current, right? So if we want to express our voltage in terms of our current, then we would have I times Z. And we're going to multiply this by I conjugate. And so this is going to look like I conjugate times I times Z, or the magnitude of our RMS phasor current squared times the impedance itself. So these guys are two other ones that are pretty handy to know because they let us calculate complex power without having as much information. So let's take these relationships a step further and see how things shake out for specifically resistors, capacitors, and inductors, okay? So we can see what roles they play in the form or contribute to complex power, okay? So for a resistance, we know that the impedance of our resistance, ZR, is just R by itself. So that tells us that our complex power is simply going to be the magnitude of the voltage squared divided by the resistance, or the magnitude of the current squared multiplied by the resistance. Effectively, we're back to our DC relationships. V squared over R or I squared times R. Okay. So what can we infer from this relationship? Is there any imaginary part of this at all? Nope. So resistors absorb average power. That is their job in a steady state sinusoidal system. For an inductance, the impedance is j omega L. So we would have the magnitude of the voltage squared divided by negative j omega L, because I have the conjugate of the impedance in my denominator. What is 1 over negative j? What was that, Aiden? Positive j. So this is just j times the magnitude of the voltage squared over omega L. Okay. I'll do the current one down here. So that is going to be the magnitude of the current squared times j omega L, or expressed slightly differently, j times the magnitude of the current squared times omega L. So what do inductors do? Well, we can see that the complex power in both cases, whether we're dealing with just in terms of voltage or just in terms of current, is purely imaginary, right? Is it possible for omega times L times the magnitude of the current squared to ever be a negative number? No. So inductors' job is to absorb reactive power. And then lastly, for a capacitor, ZC can be written as negative J over omega C, where that negative J in the numerator is simply 1 over J to put it in the form that we are used to seeing. Okay. So when we have things only in terms of our voltage, that's going to look like the magnitude of the voltage squared over positive J over omega C. Again, I got rid of the negative sign because I'm performing the complex conjugate operation on this rectangular form complex number, which just changes the sign on the imaginary part. And so 1 over J looks like negative J. And my 1 over omega C looks like an omega C in the numerator. So we have negative J times the magnitude of the voltage squared times omega C as our complex power. In terms of current, we are going to have S is equal to the magnitude of the current squared times our impedance, negative J over omega C. And so rewriting that slightly, we'll have negative J, assume magnitude of the current squared, times 1 over omega C. Or I could just as easily put that as over omega C like that. So once again, we have a situation where our Complex power is purely imaginary, but now it's always imaginary and always negative. So capacitors supply reactive power. And those are all of our complex power relationships. So I understand fully that we have not worked a single example problem at all yet. All I have done is just throw relationships at you left and right. So I think maybe today we work the in-class assignment together. This is related on average value and effective value. This is the stuff that we covered in our last class meeting. I'm not going to worry about that. I'll leave those for you guys. Let's go down here to the more fun, complex power related things. Okay. So in problem 2, we are asked to compute the complex power in polar form drawn by a certain load under various conditions. Okay. So for part A, we are told that the load draws 100 watts. So if I'm telling you that the load is drawing 100 watts, what part of the complex power am I talking about? Average power, okay? So we're told that P is equal to 100 watts, and we have a power factor of 0.75 lagging. So with just those two pieces of information, I'm expecting us to be able to compute our complex power, okay? So let's look back here and scroll up when we were talking about our mathematical relationships for power factor. So power factor is the ratio of the average power to the apparent power, and that is equal to cosine of our power factor angle. So I can manipulate just this one equation. Let me put a box around it as well because it's rather important. I can manipulate this relationship and find that our complex power S, which is just going to be the magnitude of S with an angle of theta S, will be our average power divided by our power factor with an angle of the inverse cosine of our power factor. All of that comes from just manipulating that power factor relationship. Okay. So we would have 100 over 0.75 with an angle of inverse cosine of 0.75. If I put this into my calculator, I get 133.333, angle 41.4096, so let's call that 410 degrees. And because we're dealing with complex power, my units should be volt amperes. One thing that I want to bring to your attention is the inverse cosine function on your calculator is always going to return a positive angle, okay? So we need to pay attention because we were told that our power factor was lagging. That means we know that our angle should be positive. So I'm going to put a little plus sign out here to remind myself of that. If we are ever told that our power factor is leading, we're going to have to explicitly put a negative sign in front of our inverse cosine operation to make it give us a negative angle. Okay. So just being very, very clear about that. So anybody have any questions, comments, or concerns about how we dealt with part A? All right. So for part B, we have a current of 9 plus J5 amps RMS and a voltage of 120 angle 32 degrees volts RMS. So how are we going to calculate our complex power? V times I conjugate. Exactly right. So that is going to look like 120 angle 32 degrees volts RMS times 9 minus J5 amps RMS. And for what it's worth, if you don't remember how the conjugate operation works, there's a button for it on your calculator. So I got 1,235.476 with an angle of 2.945 degrees volt amperes. Any questions about part B? That was literally just direct application of the most basic equation. Okay. Part C. We're told that the load draws 1,000 watts. So once again, what does it mean when we're talking about watts? Average power. So P is equal to 1,000. It draws 100 VARs. So when we're dealing with VARs, what part of the complex power are we talking about? Reactive power. So Q is equal to 100 VAR. And we're also told that it's operating at a leading power factor. Okay. So a leading power factor means that theta S is a negative quantity. Okay. Just to go back to talk about where we covered it. So leading power factor means theta S is between 0 and negative 90 degrees. So is our reactive power positive or negative? If we want theta S to be a negative angle, it has to be negative. Absolutely right. So negative, and I'm going to put a little note here, because leading. Okay. So S is nothing more than P plus JQ. So that's literally just going to be 1,000 minus J 100 in rectangular form. Or 1,004.988 with an angle of negative 5.710 degrees volt amperes in polar form. Actually, 7105 should be 711. Okay. And then lastly, we're told the load draws 450 volt amperes. So what part of the complex power are we talking about there? So Does it have a phase angle? That just says 450 VA, no phase angle. Apparent power. So our apparent power is 450 volt amperes. And our power factor is 0.65 lagging. I want you guys to tell me what to do here. Because I'm partially expecting a mistake. No clue. So we're in all of these, we're solving for complex power. So based on the information that you're given, this is similar, but not the same as part A. Okay. In part A, we scroll up a little bit more here. You were given average power and power factor. Now you're given apparent power and power factor. So what's going to change from our process that we use for part A? Exactly right. We don't have to do average power over power factor because we were given the apparent power. So there's no need to do that extra step, right? So this is literally just going to be S is equal to the magnitude of S angle inverse cosine of our power factor. Absolutely right. So that's going to be 450 with an angle of inverse cosine of 0.65. $450 angle 49.458 degrees volt amperes. Should that phase angle be positive or negative? Positive. Why? Because it's lagging. Absolutely right. Okay. Good job. All right, let's see. Actually, before we move on from this problem right here, did anybody have any questions about this? For what it's worth, you can expect some problems literally just like this on the test. If you look at the old practice exams and all of that kind of stuff, there are some just simple, straight calculation problems where I'm just giving you one or two pieces of information and you have to use those one or two pieces of information to either compute complex power, average power, reactive power, power factor, all of that kind of stuff. But if you can find the complex power, you can find any other part. Okay. All right. So in this problem 3 right here, we're given a source voltage that is an RMS phasor. I'm pointing that out because on some of your homework problems, you're going to be asked to do complex power-based calculations, and you're just given a phasor. So you're expected to know how to convert from a phasor to an RMS phasor. Just divide the magnitude by square root of 2. That's it. And then do your complex power calculations. All of these are based on RMS phasor relationships. Okay, anyway. So we've got our source voltage here, and then we've got our impedance ZA, ZB, and ZC. So the first thing that I'm going to do whenever I have anything like this is I'm going to use my calculator's memory to my advantage. So I am literally going to go in and put 2 angle 15 and store that as variable A. 10 minus 5I and store that as variable B. and 8 plus 6i and store that as variable c. Okay, just so that I can be lazy. So I'm just going to make a note here. This is A, this is B, and this is C. Okay. So we are asked to determine the average power absorbed by ZA, apparent power absorbed by ZB, reactive power absorbed by ZC, and the power factor at which our source is supplying power. So let me go through here really quickly and define some quantities, okay? So I'm going to define the voltage drop across impedance ZA, positive polarity on the left, just arbitrarily, literally doesn't matter at all. And I'm going to define this current as my RMS phasor current IA. Pretty similarly, I'm going to have VB and IB and VC and IC. So if I know either voltage or current across any of those impedances, I have enough information to calculate complex power. To calculate the complex power for my source, and it says specifically here, supplied, I want the current that's flowing into the negative polarity terminal. So I'm going to call this IVS. So for my impedances, I need either voltage or current. For my source, the only thing I need is current. So how could we analyze this circuit to get those quantities? Voltage division to find what, or VA as well. So we could use voltage division to find any of those voltages, okay? So let's use voltage division to find VB and VC because they're the same voltage. Those elements are in parallel. Are we okay with that? Okay. So using voltage division, we could say that VB is the same thing as VC because they're in parallel, and that's just going to be VS times ZB in parallel with ZC over ZA plus ZB in parallel with ZC. So that would be, let's see, VS was 120 angle 45 degrees, volts RMS. ZB was 10 minus J5. ZC was 8 plus J6. All over. ZA was 2 angle 15. And I'm just going to put here plus numerator so that I don't have to write all of that out again because it is literally what's in the numerator. Are you all okay with my lazy approach here? Okay. So 120 angle 45. So that is B times C over B plus C over A plus B times C over B plus C. When I put that in my calculator, if I put it in correctly, I got 90.896 and some change with an angle of 43.082 degrees. Volts RMS. So we have enough information to go ahead and knock out part B and C already with that one bit of analysis, right? So for part B, recall that the complex power absorbed by impedance ZB could be written as the magnitude of our voltage VB squared divided by the complex conjugate of our impedance ZB. That was from our alternative relationships that we developed. So that's literally just going to look like 90.896 volts RMS squared. We only want the magnitude, so we throw the phase angle away. It's not important to us. ZB, it was 10 minus J5. So ZB conjugate is 10 plus J5. So I'm going to do this the laziest possible way. So I want the magnitude of my previous answer squared divided by the conjugate of what I have stored in my calculator as B, so that there is no chance of me typing anything in wrong. I'm letting my calculator do all of the work for me. I got 738.985 with an angle of negative 26.565 degrees, volt amperes in polar form. And 660.968 minus J 330.484 volt amperes in rectangular form. We were asked to determine apparent power. So which of those four numbers is the correct answer? Apparent power is the magnitude of the complex power written on the board, for what it's worth. Right? So the part that we're looking for is actually this guy right here with units of volt amperes. For part C, something pretty similar. So that could be the magnitude of VC, excuse me, which is the same thing as VB, over ZC conjugate. So 90.896 volts RMS quantity squared. Let me scroll up here. So 8 plus J6 conjugate is going to look like 8 minus J6. So the magnitude of what I just stored is X, because I didn't remember that I was going to need it again, over the conjugate of C is 826.210 with an angle of positive 36.8698. So let's call that 870 degrees volt amperes in polar form, or 660.968 plus J 495.726 volt amperes in rectangular form. we are asked to find reactive power. Which of these four numbers is the reactive power? The 495. And this guy would need units of volt amperes reactive. So now that we know VB, we could easily determine VA by just doing KVL around the left-hand loop. Or we could find IA by effectively just doing Ohm's law. So since we haven't used that current relationship yet, let's find IA really quickly. So using Ohm's law, IA is just going to be VS minus VB over ZA. Let me scroll up just so that you guys can make sure that that is correct. It is, by the way. So if we're okay with that being the expression for my current IA, then that's going to look like 120 angle 45 degrees volts RMS minus 90.896 angle 43.082 degrees volts RMS all over 2 angle 15 degrees ohms. Let me just double check that that is correct. It is. So 120 angle 45 minus what I have stored as X over what I have stored as A gives me a current of 14.6565. So let's call that 14.657 with an angle of 35.957 degrees amps RMS. Solving for part A, SA is going to be the magnitude of IA squared times ZA. Because I'm running out of room, I'm not going to write down all of the numbers. So that's going to be the magnitude of what I just stored in my calculator as Y squared times what I have stored in my calculator as A. And I get 429.6292 angle 15 degrees volt amperes, or 414.98999. So let's call that 990 plus J 111.196 volt amperes. We were asked to calculate average power. So which of those four numbers is average power? 414.990. And what should the units be for average power? Watts. Okay. Does that match? I'll be damned. And then the last thing we need is our power factor at which our source supplies power. I'm going to do that calculation up here since I ran out of room at the bottom. So we could say that IA is the exact same thing as the IVS that we're looking for because they're the same current in the same direction. So no need to do anything fancy there. So, excuse me, the complex power for my voltage source is just VS times IA conjugate. So 120 angle 45 times the conjugate of what I have stored in my calculator as Y. And I get 1758.787 with an angle of 9.043. In rectangular form, that's 1736.926 plus J 276.438. So how would I calculate my power factor? We could take average power over reactive power. Nothing particularly wrong with that. I 99.9% of the time do not use that relationship. Instead, cosine of that angle. So cosine of the polar angle of my prior answer, because my calculator can do all that. Again, I'm typing in as little as humanly possible. And I get oops, change this color back. 0.9875. So let's call that 988. Is this going to be leading or lagging? Why? Because the angle is positive. So we got 20 minutes left. What do you guys want to do? The first problem. Okay. Or think about our feelings. Equally valid. Okay. So for the average value here, I feel like we can literally just look at the graph and figure it out. So half the time it's above 2, half the time it's below 2. So VA average is 2. And for part B, just by inspection here, it looks like half the time it's above 7.5 and half of the time it's below 7.5. So VB average looks to be 7.5. To find our effective values for part B is going to be much easier than part A. So let's do part B first. Okay. So to me, it looks like our period is 4 seconds. Anybody have any beef with that? So VB effective is going to look like the square root of 1 over 4 seconds times the integral from 0 to 2 seconds of 5 volts squared dt plus the integral from 2 seconds to 4 seconds of 10 volts squared dt. Is going to equal to 1 over 4 seconds times 25 volts squared times 2 seconds minus 0 seconds plus 100 volts squared 4 seconds minus 2 seconds. And I think that is enough where I can just throw it in my calculator. So let's see. 25 times 2 plus 100 times 2, all of that over 4. Take the square root. 7.90569 volts RMS. Any questions, comments, or concerns? Okay. So part A is going to be harder. I'm going to do it the quote unquote hard way. And then I'm going to use that to actually give you guys a relationship that you can use for your homeworks to make things much easier. Okay, so that's the reason I'm going to do it the hard way, is to explain how the easy way comes about. Okay. So if we were to mathematically describe this function here, VA of t, we can see that there is a 2-volt DC offset, and then we have a what looks to be a sine function to me. So I'm going to put plus sine. Just to be clear here, that's 3, and that's 1. And the period is pi, so t is equal to 2 pi over omega, which means that omega is equal to 2 pi over t. So 2 pi over pi, so sine 2t volts. Are we okay with that? I don't believe I've used any kind of new relationship or anything. So because we're not used to dealing with sine functions so much, I'm going to call this 2 plus, cosine 2t minus 90 degrees volts. Are we okay with that? All right, so let's get down here and do some gross math. So this is going to look like the square root of 1 over pi seconds times the integral from 0 to pi of 2 plus cosine 2t minus 90 degrees volts quantity squared dt. So that's just me using my generic equation, 1 over pi times, 1 over t times the integral from 0 to t of the voltage squared, take the square root of the whole thing. All right, so now I need to square that thing, and this is where the math is going to get a bit gross, okay? So 1 over pi seconds times the integral from 0 to pi seconds. So 2 times 2 is going to look like 4. Let's not worry about the units here. We know it's going to come out, since it's a voltage and all of that kind of good stuff, and we're squaring it, it's going to be volts squared, and then we're going to take the square root of it to get volts at the end. So 2 times 2 is 4. Then I'm going to have plus, so I'm going to have cosine, this cosine thing times 2, so that should all, overall look like 4 cosine 2t minus 90 degrees. And then I'm going to have cosine squared 2t minus 90 degrees, like so. So before we move on to our next step, did I FOIL that thing out correctly? I think I did, for what it's worth, but I just want to make sure, because this is the type of place where it seems like I would make a mistake, just to be clear. Okay, so now I'm going to apply that trig identity so that I can make my cosine squared look like cosine functions, right? So square root of 1 over pi s, integral from 0 to pi. So I'm going to have 4 plus 4 cosine 2t minus 90 degrees plus 1/2 plus 1/2 cosine 4t minus 180 degrees. We could break this thing up into 4 smaller integrals. So I want you to put in your calculator what the integral of 4 cosine 2t minus 90 degrees is from 0 to pi. So I'm integrating from 0 to pi of 4 cosine 2x minus 90. Actually, I need to fix that because I'm going to be lazy and just call this sine 2t so that I don't have to worry about phase angles in degrees and angular frequencies in radians. So 0 to pi of 4 sine 2x. What did you guys get? 0. This guy right here, 4 cosine 4t minus 180 degrees, is just the same thing as negative cosine 4t, right? So what's the integral from 0 to pi of cosine 4t? Also 0. So the only thing that survived was this guy right here, which is our DC term squared, and this guy right here, which is actually the effective value of our AC portion squared, right? So this is going to be 1 over, let's see, square root of 1 over pi times pi times 4.5. 2.121 volts RMS. I apologize for not having units of volts RMS here for the effective values. I definitely should have. But anyway. Okay. So that was not too bad, but some of the questions that you were given on your homework assignment dealing with similar things are quite gross because they have more than one sinusoidal term that you have to square and all of that kind of stuff. So let me give you a cheat sheet effectively, okay? So we could say that, so let's say that I have 4 V of t is equal to Vm1 cosine omega 1t plus theta v1 plus Vm2 cosine omega 2t plus theta v2 all the way out to Vmn cosine omega n t plus theta Vn plus VDC. The effective will be the square root of VDC squared plus VM1 over square root of 2 squared plus VM2 over square root of 2 squared all the way out to VMN over the square root of 2 squared. This is nothing more than take the effective value of each part, square it, add them all together, take the square root of the result, where the effective value of a DC term is the DC term itself. And the reason why this works is we just saw that we're going to be integrating effectively over integer multiples of intervals for all of those terms that happen when we square those sine and cosine functions and all of that kind of good stuff. So everything, the only thing that's going to survive when we apply that trig identity is actually just the effective value squared.